Okay, so we are wrapping up more or less multiple integrals. I brought up this example of how triple integrals or double integrals could be applied, and the challenge so finding the volume of the amount of water in the bucket with known dimensions. When it's about to it's tipped and about to start to lose drip water dripping out. So then you got to represent the triple integrals. You have to represent it in this manner with multiple surfaces involved, which is we'll talk a bit about that now. But it does seem to appear. It occurred to me that this will be. You can actually guess what the answer is. What?
Is it half?
Yes. If you think about it, you can flip it over, and there is as much air in the bucket as water, right? So if you turn it over, then it's like turn it over upside down. It's as if it is air that is starting to drip out of the bucket. Okay, so that certainly works out, but you realize that as soon as you lose some of the symmetry of the bucket, then that idea also comes out. So either it has shape like this. Okay, so once again, it's not necessarily going to work. Or imagine like a box filled with water. Once again, so if you put it on a corner, then it's different from when you put it on the side. If it's on the side, you still. The rule is actually, now I remember that it is if you see the bottom, right top of the bottom, then it is half. But there's conditions on the symmetry of the vessel that only allow for that to happen, to have this shortcut. So the point, of course, of all of this development is that we can handle anything with or without shortcuts. So whether it has any kind of symmetry is not necessary for us to solve the problem, and that is calculus 2 early on computations of volumes of surfaces or lengths. No, not lengths, but lengths too, as a matter of fact. They were limited to particular cases of either shapes or curves, surfaces, and so on. And now it's not. So, for example, you might remember that the parametric lengths of curves were computed, yes, but only for curves that represent functions. Now we can compute them for any parametric surface, or parametric curve. Furthermore, areas are also computed only in calculus 1 for these. And now we can compute any area, and now we realize that the areas are double integrals. Okay, same with volumes. We were able to compute some of the volumes up until now as double integrals, and now we realize that all volumes are triple integrals. Okay, so what followed here, everything related to Frobenius theorem, is really about specifics of how that idea is carried out for particular, not as narrow as it used to be, but particular shapes. Okay, so we started with Frobenius theorem for a box or a square or a rectangle in dimension 2 for double integrals, and now we take it beyond, so this is the double. Here it is. What is a double integral can be converted into when the origin of integration, the domain of integration, has a particular shape, and the particular shape being like on the previous page, right here, it is squeezed between two graphs of y, function of x. Okay, so in that case, as you can see, these four entities, numbers here and functions there, serve as the limits of integration. Okay, so on the left we still have our Riemann integral defined through limits of Riemann sums. On the right is actually the computational formula. It is why computational? Because it only requires you to know calculus 1 integration. Okay, and then that works out. That is the origin is as general as it gets for the time being. And in the meantime, we only had one example, but should be enough. And the example was of the sphere, and that's exactly what we have carried out. So we took the half sphere, even though we could have taken the whole thing. Wrong about that. It is the function was given by the half of the sphere. It's inside of the integration. Okay, and then the limits on the xy plane. Okay, so this is the z. Okay, and the four limits are of the Fubini theorem, and they are referring to the xy plane. And once again, x is natural. Okay, no restriction on the value of x, because we treat x as if it is an independent variable. Okay, so and the y depends on x. So that's that picture on left gives us that dependence. So limits of x are just two numbers, and limits of y are depend on x. Okay, so if x is given, then you know the limits for y like this, and it is different for different locations. But so this was just an example of Fubini's theorem that is how it is applied. And the challenges, as I mentioned, is finding the domain of finding this representation. Okay, so this is the original representation of the sphere is that equation over there. But really then break it apart and representing it as what amounts to four limits of integration is the challenge. Okay, so now moving on to triple integrals. Triple integrals, which will be very similar, but we could actually once again take. Well, the idea is as we progress from. Let me make that point clear. So Calc 1 areas are single integrals. Okay, and now Calc 3, yes, but only for some special shapes. So in other words, this one. The area of this kind of area is indeed a single integral. Okay. Now we know that we could handle something like this with a double integral. So this time the answer is areas are double integrals. So the area of this, say this is region R, and so area of R is equal to double integral over R. That's it, of 1. Okay? So that is four-dimensional 1 for areas, and now we can no, okay, so it's not calculus 1 anymore, it is early calculus 3. And as early meaning last week. Calculus 3. Volumes are, what are volumes? In the example we just saw, the volume of a sphere was what?
Triple.
No, the way we have discussed them were they have been so far, as you can see, double integrals. Okay, and now we make the next step, and we realize that they are triple integrals. So volumes are double integrals, or have been. So it's specifically, and then well, we say in calculus 3, we say yes, but only special shapes. And by special shapes, I mean what we just discussed a minute ago. Something like this, surface like this. So volume like this would be, the volume is, or has been, volume is a double integral of f of xy dA over, say, R. So this is R, and this is z equal f of xy. That's how we by analogy, total analogy with the previous example, this is y equal f of x, and we talked about area, so some region is bounded by the graph of a function, okay? Function of one variable right there, and function of two variables here, okay? So the function is integrated over its region of integration. Could be some weird shape, or it could be circle, and then that gives the volume. Okay, now we go beyond that, and in general we have the volume of region, say W, is equal to triple integral over the W1 dV. Okay, so this applies to any shape of any solid in dimension 3 of any shape. Okay, so it's the same thing. We'll just see in a minute how that indeed these two match. Well, if you remember how we match them in dimension 3, dimension 2, or rather double integrals, we do pretty much the same thing. So except it's like for the previous pair of this comparison. Remember how we realized that is in fact a double integral because we're integrating over that region. We're integrating a function of equal to 1, and that gives us simply the volume of a region with the base, or in thickness 1, which is its volume is the area. Okay, so we don't have this luxury of using one extra dimension to understand it, but then we just think about 1 as we have as what? In triple integrals, what's the interpretation or metaphor for the function? So what do we integrate? I mean, if we want one step outside of the abstract mathematical understanding of function of triple integrals, what is the meaning of the function of integration, and what is the outcome of the integration? Well, we did it with the box. Remember what was in the box?
Was it the density?
What?
The density.
That's right. The answer is the density. Yes. The answer is the density, and then the output is in fact the mass, weight, but if the density is 1, the answer is volume, right? So that's all there is. Really, that's what I was referring to. So that's extra. That's 4 dimension that we don't have to use around here. So we use the just a value of our choice. So we choose density, and then this is the metaphor for the triple integral of a function is that function is density, and the output of the triple integral is the mass. Okay. So then if we really only interested in the volume, then we just assume that the density is constant equal to 1, and then we have this. Very, very simple formula. Triple integral is of 1 over region is equal to, is the meaning, and I don't want to read it from right to left, but read it from left to right. You can think of this as the definition of the volume, as well as this one is the definition of the area. So definition of the area, definition of the volume. Area. Okay, so well, here we go. Okay, so let's check if this is how well this is understood. What about dimension 1? So triple integral, double integral. What's about single integral? Well, let's try it right now. So analogy should be very simple because it's simple where you're going down, not up, but down to pretty much the calculus 1. So what are we talking about? It's not volume, area. What's next down there? Length. Okay. So length. Okay. So some L of some R. Okay. I don't know what R is. length of, I don't know, okay? What's next? What kind of integral is it? Single over q of 1 dx. Okay, so can you explain what we have here? So we're defining the length of what exactly? Well, it's really not the definition. This is the q could be only one thing that is of any meaning in the one-dimensional case. Is it's simply an integral. It's simply the integral, say a b or something like that. Okay, so and then when you integrate single integral from a to b of 1, the answer is b minus a. Here we go. That's right. Okay, so it all makes sense. The hierarchy of integrals, as well as hierarchy of dimensions, hierarchy of geometric entities, curve. It's really not much of a curve, but because it's a one-dimensional case, that's what we can do. Lengths, areas, volumes, and then we keep going there. However, the meaning becomes less tangible, and so what is a quadruple integral is the four-dimensional volume of a four-dimensional solid, whatever that is. Okay, so this will do, so it is a starting point. It helps us to understand certain things, such as how units fit into this. So that over there, that has a perfect meaning. The V stands for volume, A stands for the area. We don't have, in dimension 1, we don't have anything like that, but that's okay. So units they match. So volumes will be triple integral. If you measure everything in cubic feet, then well you have triple integral. When it is square feet, you have double integral. Okay. So what remains is to also discuss how it fits into this. I think I brought it up a little bit shortly ago. Is the average value? The average value of the function would be. I'm not sure how much I said last time, but well, actually, first of all, a triple. Well, let me just take this notation. So for n equal 1, 2, 3, or maybe higher, in our n, we have a notation for all integral. Say integral w f x dx. So x in our n, and w also a region. So x is a point in Rn. So f is a function of n variables, okay? And w is a region in Rn, okay? And then we could speak of then what is the meaning of this integral, which I simply, as you can see, the difference is you do it sometimes beyond 3. You don't want to repeat those integrals anymore. So what do? You use 1, okay? So and then the context. This is the context. It will tell you where you are and what kind of integral it is. So if n is equal to 1, you have a single integral. Naturally, n is equal to 2, you have a double. And you could go back if you know, you write 2 integrals. N is equal to 3 is triple. And once again, you can, all of that have meanings of their okay? But if you want to handle them all simultaneously, and that is certainly worthwhile, even if you stick with only dimension 1 to 3, it's still worthwhile. And if you go beyond, it is even more worthwhile because the functions, even though the interpretations fall apart in terms of volumes or areas, what remains what is a very natural thing to ask is about the average value of a function. You can have easily a function of all kinds of variables, and what is the meaning of its average? And the average is, so if you remember from calculus 1, the average value of y equal f of x over integral AB is what?
So 1 over b minus a
Yeah,
times the interval from a
integral
to
from A to B. I'll put it this way. Okay, so that is calculus 1. Now, some short time ago, we defined the average value of, now this time, function 2 variables over, initially it was over a rectangle. Okay, so we can do better now. So the function could be defined over any region. So over a region, say U. Okay, remember how it switched? We just filled everything else outside of the region with zeros up to a certain rectangle. So then, similarly, you can have double integral, and then so what's the answer? So how do you average? Well, one thing to understand, I suppose, is in this, if you have a function, you can think of it as density if you like, but generally speaking, you can say that these values are distributed within certain regions. So these are the values over there, how high you go there, these are the values of the function, or here, there once again, how far it goes, the values are distributed. If that value is the density, then we speak of the total value of the density, which is simply which is the mass. So from the distributed value through the region, we go to the total value. So all of these three can be thought of as the total value of the material inside of a certain container of a possibly irregular shape. Okay, so the weight is distributed, and the distribution of weight is given by the density, just a different word for it. And then when we integrate, we collect it all together, and we have one number. Okay, whether it is a length, area, or volume. Or in n-dimensional cases, you can see this is the total value of f in W. That's the meaning of it. And when you have the total value of a function of a value, then what is the average value? Well, think about this by analogy, thinking with this. This is how we average. We take the total value and divide by what? We divide it by the region, what? Over it's not the region. The region is not a number. B minus A is a number. So this is the length. Okay? So if this is the length, and we are ascending dimensions, then what are we going to get here?
Area.
The area. Okay, so area of U, F, D, A. Okay? So that's the average value of a function of two variables will be the total value, which is the double integral, divided by the area. As simple as that. Right? So once again, that analogy works of like you have a sandbox and in a dimension, and then what you do is it's so filled with sand, and then you do not change the total value of you level it out, okay, with something. And then, but you do not remove anything, add anything, so the same amount, the total amount of sand remains the same, but what if it is leveled? Okay, so if it is leveled, the same amount, then this height will give you the average value. Okay, so this illustration is one-dimensional for that calculus 1 idea, but really if you look at the three-dimensional sandbox, you just from a side, and then you have pretty much the same idea. So you divide by the area, okay? And then you keep going, and then you have the average value of three variables. So U is equal to f of x, y, z over say W in R3, so this was in R2, and this interval naturally was in R. Okay, so, and once again, so we know where we're going. We are going with the, what? Volume of that region, and triple integral over W, F dV, which is our integral of triple integral function of three variables. It looks very similar. So once again, this is just to remind you that this is the area and this is the volume. Okay, so and then you can think of this certainly if you go back to the density. The function is density. The triple integral is the literally volume of your solid. Okay, you end up with the average density. So if F is actual density, then the whole thing is average density. Okay, so that is the idea. Okay, so and then if you have a function of if you have a function of 100 variables, how do you average it? So I know U is equal to F of X, X in R n. Okay, so what's the average? Over region, once again, region W in Rn. Okay, so n integral over the same W. So once again, since when you have n integrals, you don't want to have n integral signs, so I just have one. As long as I'm specific, I said over there that my region lies in Rn, so we know that this n-dimensional integral. I know that the variable of my function is also has n variables, and I can write it this way, which is fine. The only really remains to be determined is what the denominator is. So how about I just put dW here, and then we'll try to figure out what it is. So what is it? So it is kind of an n-dimensional volume in some sense, but what is it computationally? So it's n volume, if you like. What is it equal to? How we compute n-dimensional volumes?
We wouldn't want to put n minus 1 integral signs, but if we wanted to represent it as an integrated...
No, it will still have n integrals. What matters is what is the function, what do we integrate?
1 over dx, or 1 dx.
1 dx, right. So, okay, so every time that this is being repeated again and again, length, area, volume are computed by integrating the function equal to one constant function over that region, and that gives you the what you want. And in this case, we just follow by analogy of what is the amount of how do we measure the size of our domains. To make an average, we have to divide by the size of our domain. When we know we are out of dimensions, out of some tangible quantities that we can use and divide by. So we come up with, we already know what the meaning of that volume should be. It's simply the integral of function 1, and then so we compute the n-dimensional integral of a whole function divided by the integral of a function when the function is equal to 1. Okay, and that will be the average. Okay, so the only thing that remains here is to, I guess, mentioning the Fubini theorem. So let me go back with this a little bit to the last Fubini theorem, which was two-dimensional. And now let's think about what a triple dimensional integral would look like. So let me so this was integral over r. I didn't mention it, but it was in R2. And now we're moving on. So I'll start to insert things. So now we're talking in R3, and it will be a triple integral. The function then is a function of 3 variables. Then this will be z over here. Okay. So origin is an xz space. Okay. So once again, the idea is to convert it somehow, the triple integral of origin under good circumstances that we can handle. So there's some special origin into consecutive integrals. There are going to be 3, right? So okay. So what should we do? So it will be, our origin is x, y, z, and the limits for x are between a and b, as you can see over here. Okay, over here. Okay, then the limits for y lie between 2 curves on the xy plane, right? Okay, so that creates a 2-dimensional origin as we saw it. But now my origin is supposed to be 3-dimensional, so there will be more here. Over here, I have to continue on to have to give the limits for z. What do you think those limits should be? So first of all, this is not the domain integration. This is not the domain integration. This is the whole thing. So let me make that clear. I'm talking about this is my domain integration. Okay. So my 3-dimensional solid here is my domain of integration. And this is the challenge, really, to represent something like that in the form of limits, separate limits for x, y, and z. Okay, so suppose we already have the limits for x, y, and x and y. What are the limits for z in this picture? So forget about the integral. What are the limits for z?
Would it just be something like f1 of y to f2 of y?
Almost. This you're referring to this surface about as f2 of y. But do you want to correct your f2 of xy? Right, because it depends. This is a surface, so it depends on x and y. So I'll put it. I'll use h just for convenience. And this is it. So this one is the top one is h2 of xy, right? So z equal f of xy, and then there's a possibly bottom surface here bounding the whole thing. Somehow it will be z equal h1 of xy. Okay, so this is how it works out indeed. So our origin, that is, we can handle with Frobenius theorem, or the approach is, once again, it starts the same exact way what's in blue over there. So x and x is a given integral. It's the most independent variable of 3. We create kind of a dependency between x and y and z, and the x is totally independent. Then y, it is kind of depends on x. Okay, the limits for x, if we're staying, for y, if we stay in the xy plane, are those two functions g1 and g2 right here. Okay, and then we move to z, and this time z depends on x and y. And the limits for z then are 2 surfaces from below and from above of our origin, and they are h1 of xy and h2 of xy as well. And then that creates an integral. Well, once this is established, this is the hard part to figure out what the limits are. And then we're moving on to and just insert extra integral on right. I already inserted one on left, and now I just do it on right. Okay, so let me try to. So what should I put here? So this will be still d y, and inside there is more. Okay? So in the middle, what do I have in the middle?
The integration from h1 xy to h2 xy.
That's right. Well, it's kind of complicated, but really not that bad. It's just cumbersome. And I integrate the same function of 3 variables. Okay? So, so once again, do you remember the picture? So there, the first thing happened on the x-axis, in an interval. On the xy plane, it is a region bounded by 2 curves and 2 straight lines. And then finally, in the 3-dimensional space, the whole thing is bounded from below and from above by 2 surfaces, h1, h2. Just to illustrate this, let's quickly represent what we already have computed. That is the volume of a sphere. Once again, sphere, we already know. And let's just have A, B, all of these 6 parameters in order to represent it. So let's say radius r, just to make it slightly more complicated. So so it looks like this. No, this time I'm not going to do half. We did half. Remember, we did computation, and we computed the upper half of the sphere. So I'm not doing that anymore. I'm taking the whole thing. Okay, so we know that the volume will be the triple integral of the sphere itself. So let's say call it still W of 1 dV. Okay, and so now we want to apply for being a sphere in order to handle the actual computations. So okay, so this is the formula, and this is one what's I highlighted here is what we are after. In order to apply it, we have to represent our sphere with these 6 quantities: A, B, G1, G2, H1, H2. Okay, so let's go. This is my x, y, and z. The good news is we start pretty much the same way as last time. So let me erase this. Let's go straight to W. So W is represented by x, y, and z. So we are looking for the limits for x, y, and z. So limits for x are, so let's take a view from above. Okay. What are the limits for x?
Negative r and r.
Negative r. All right. For y? No. That will give a rectangle. If x and y, if limits for y are, say, also constant, it will give us a rectangle, or a square in this particular case. So the limits come from all the shapes. So I'm looking right now at this circle, which is, of course, x squared plus y squared is equal to r squared, but really we have to look at it separately, upper and lower halves. Right? So this is upper half, and the equation is y equal
radical r squared minus x squared.
R squared minus x squared, and that's where it goes. And the lower is the same thing with negative sign, and that becomes my lower limit for y. Okay, and then so that takes care of x and y and the xy plane, and now we're looking at well, I don't want to make that point clear. I tried to do it last time, but once again, once x is fixed, that's how we determine. We progress it one dimension at a time in that order, x, y, z. So x is independent runs between negative r and r. Then we progress how? We fix x. So we fix x, and then look at the limits for y. And the upper limit will be r squared minus x squared square root, and the lower limit will be negative r squared minus x squared square root. Okay? And then we progress beyond this. This time we fix x and y, Okay, now in this picture, so x and y is fixed, so some location on the xy plane is determined, and then we're going vertically, this time, actually third dimension like this. Okay, and until we hit the surface. Okay, and that is, that bar is in fact my limits for y, for z, whenever x and y are fixed. So I picked xy point over here, and then I go up from that direction until that straight line intersects the surface, and the upper and lower intersections will have different meanings then, right? So this one is, what is this? xy is fixed once again, so xy is this point over here. xy is fixed on the xy plane. So the equation of the plane, in case you don't remember, of the sphere, xy plus y squared plus z squared is equal to r squared. Okay, so x and y are fixed, which means that you express simply z in terms of those x and y, and it will be what?
Medical r squared minus x squared minus z, or
That's right.
y squared.
You remember we did almost exactly the same thing last week. It was a double integral, and and we only were doing half of it, half of the sphere. So we only needed this limit, but we all had all of these 5 limits appeared, except the last one. This one I'm about to write. It served as what? Do you remember what it served as? They used to be what? Last week? Same exact computation almost. It was a double integral, so z was not taken care of by limits of integration, but rather by what? By the function. We integrated this function over that region. Remember now? Okay, so it used to be the integrand. Used to be last week, but that was a double integral. Now it's a triple integral, and then when you have only we have an integrand and you have one function, then we did speak of the solid line of the graph. Solid line of the graph. So that was the graph, okay. And it between the xy plane and that graph, we talked about half of the surface, and we computed it. And now we have 2 halves, and then I have at the bottom, which is pretty much the same over here, so it will be negative r squared minus x squared minus y squared. So these are the limits. This is my w. I don't really need anything, do anything else. Now, so these are the limits. There is no reason whatsoever to do this computation again, because all the computations, including the last substitution, are exactly the same. The computation is identical, okay, except the starting point is slightly different because it will have triple integrals, but that very term in the beginning will disappear, well, almost instantly, because why is that? Because we're integrating one with, well, let me write that. So inside, that's what we have. We integrate 1 with those two limits. So it will be from negative r squared minus x squared minus y squared to positive r squared minus x squared minus y squared dz. Okay, so and that's not hard to compute, right? So what is going to be? So I integrate 1 with respect to z, so I'll have z with these limits, and then I subtract them, but it's the same thing, so it will be twice. Okay, and then I'm left with those 2 integrals to taken care of, but that's exactly what we did last time, and it works out to the same. Oops. and 4 pi over 3 r cubed. So the only difference is that little 2 over there is the only difference from last week's computation. Okay, so it is challenging computationally and commonly used to compute, to ask a problem that are challenging. It require you to, solving a problem like that requires you to understand single integration, indefinite integration, definite integration, thinking two-dimensional followed by three-dimensional. So there are a bunch of challenges from all over the course come into a problem like that. So sometimes they appear, but a two-dimensional one is I'd say hard enough. This is just a more important point to make is that once again volumes are triple integrals, and sometimes we can actually carry out the computation all the way through in order to find the answer. Okay, so so what we are not, what we kind of skipping is a couple of topics. Change of variables for one, that is quite challenging. So if x, y, and z are moved away, what does it do? X's and y's are stretched or shrunk, and maybe rotated to, and then whatever happens to the integral. It is not sufficiently discussed in Calculus 1 to begin with in order for us to make quick progress. Another topic that you saw in Calculus 2 that was very related to today's discussion, it is the center of mass. So remember, the center of mass of in Calculus 2 was of the lamina, so it was like a planar density, and now we can speak of a triple, the actual density of three-dimensional solid, and find over any kind of weird object, including this one, we can find where the center of mass is by naturally triple integration. 3 triple integrations. Okay, so we're going to do it unless we have some time left at the end. All right, so 2 more.